I believe recording is active. Okay, I'm gonna get started. So this is gonna be more like a knowledge transfer session on the hardware validation side, focus on power electronics like buck converters and LDOs. And I'm gonna go over two tests. I think these two tests are generic enough to cover the performance, to test the performance of the power, the voltage regulators, like the buck and LDOs, mainly these two. And so I'm gonna start on the first one, which is the load regulation test. Load regulation. This one kind of sucks. Can't really see it from the recording. I'm gonna try. I don't know, I'm just gonna talk. For this test, the main goal is to measure how stable the output voltage is under the load. Okay. Thanks. For all the power supplies, like the bucks and LDOs, they have some parasitic output resistance, either from the wire or from the PCB trays. So when your load is increasing, let's say from 0 amp to 5 amp, the output the voltage, the V out seen at the downstream device will drop. So for example, if you have like a 5 volts output, by the time you increase the I out, the output current to 5 amp, it might drop down to like 4.7 or 4.8 volts. And the reason we're doing this test is to make sure that those scenarios don't happen. So for example, let's say the camera board only has a camera only takes input voltage range from 4.9 to 5.1. And if the output voltage dropped below, let's say dropped to 4.8 volts, it will brown out the device and the camera will stop functioning and won't take any videos. And so we don't want that to happen. So we want to run the test, ensure this doesn't happen. So we are gonna run the test, and we're gonna observe a voltage versus current waveform around something like this. So this is around 5 volts, and then this is like 4.5 volts. I'm just making numbers up, but that's like a typical response. And this can be like 5 amp, and this is 0. And to run this test, we will need 3 different instruments. So first we'll have a power supply to deliver power to the voltage regulator, either the buck or an LDO. And then we'll generalize this voltage regulator and call it device under test, and abbreviate it as DOT. For the dots, I want to measure the V out So we'll have two wires from the V out to a voltmeter. And for the voltmeter, we're just going to use a digital multimeter, DMM, to measure the voltage instead. So we're going to use DMM. And we need something to pull the current. So we're going to use an instrument called electronic load. And abbreviated as E-load. So now the setup is done, and you might notice that the electronic load, I draw two wire connections. These are both from V out, so this is like, I should probably draw them on the same point, same node. So the V out, the positive, the power term, like the power goes to power, ground goes to ground, and this is how the current flows. Flows into the E-load and flows back out. But E-load, it can also measure the voltage across its two terminals, and if that's the case, we can eliminate this DMM here. Does anyone know why we need to use two separate two separate pairs of wires here? Want to take a guess, Ryan?
I don't know. Are there parasitics across the wire?
Yes, that's the reason. So in the wires, we have. I'm just gonna draw the dot. It's by itself. The dot and the E-load. To the E-load, we can model the wires. This parasitic resistance is big enough that we need to model it as resistors. I'm not going to draw the E-load. I'm going to draw the E-load as another big resistor. Because it's essentially just a resistor that takes the current and dissipates as a heat. So we have the power wire up here and ground. And both of them carry current, and both of them have parasitic resistance. So we have the R, say wire, and R wire. And the resistance is typically around, I would say 0.1 ohm or even less. But if you have a large amount of current, the voltage drop is significant enough to affect the measurements. So we need another pair of voltmeter here, so that it takes zero current. So the voltage at the output of this regulator is not affected. And that is the reason why we need another pair of wires to measure the voltage, the V outs. And to run this test, you can either divide it into small intervals of steps. So let's say 0 amps, and then 0.01 amps, 0.02, all the way up to, let's say, 5 amps. So in this way, you can take measurement at each point, and then you have another, maybe I'll write it down in the column. So 0, 0.01, 0.02, and then all the way up to 5. And then this is the I out. And you can also record a V out in this way. You can say 5, 5.0, 5.0, and down becomes to maybe let's make it 4.999. And down here it will be 4.5 volts. And in these situations, in using this method, we can also measure the input voltage and input current, so I in and V in. And this I in will be coming from a amp meter inside of the power supply. So inside the power supply, it usually has amp meter at its output. So we can get the input current information from here, and we can also get the power supply, and it also measures the input across the voltage across these two terminals. So we can also get the V in information. And let's say I in is 0. Sorry, no, I in won't be 0. There will be some leakage current inside the dots. Say 0.1. V in, say 12. I'm just making these numbers up, assuming this is like something like a 12 to 5 buck. And then we get each measurement at each point. And in the end, now we can measure for efficiency. So this is like we are making two tests into one test. We are combining the load regulation test and the efficiency test of the dots into one single test. And this efficiency, the formula would be P in over P out. So input power or output power, which is V in I in over V out, I out. Yeah. So this is method 1 of running the load regulation test. And then we also have another method. This one, we need to program the electronic load. So inside the electronic load, there's a parameter called the slew rate. And this slew rate is pretty much indicating how fast the signal can change. So the signals can either be a voltage signal or current signal. So it's either the change of voltage over time or the change of current over time. And inside the E-load, since we're pulling current at the output, we're going to use this parameter. And inside the E-load, we can only use the change of the slew rate is always regarding the current. So in this time, instead of discretely increase the current output, we are gonna increase like continuously, like a smoothly ramps up, like this. Say this is time. This would be current, which is I out. And this is method 2. So this straight line is method 2, and method 1 would be something discrete. So it takes some steps at a time, steps at a time, steps at a time. Like this. And I would say method 1 is more common, and method 2 is mostly used inside of those like multi-phase buck converters. So you have, this is a little bit sidetracked, but you can have buck converters like different. You can have multiple like inductors and capacitors in parallel to deliver more current. Something like that. But we are not gonna touch on the multi-phase buck converter today. Something like this stuff. Okay, and then after the test is done, if you notice there are any problems, so let's say the voltage output, the V out is too low, let's say at the maximum current, around like say 5 amps, there are two ways to fix this issue, but mainly the method is gonna be increase your V out. So let's say you have V out was 5 volts. So you can pump it up to around like 5.2 volts. So that's at the maximum V out. At Imax, the V out would be, let's say, around 4.7 or 4.8 volts, which is acceptable at the downstream devices. Okay, and that's it for the load regulation test. Any questions? Yes.
Does the inductance on the wires play a role in any of this, or is that kind of just like neglected as well?
That is neglected as well. That's usually the inductance of wire is too small, so we can ignore them. And yep.
I got a question.
Okay, you go
Oh,
first.
sorry, I can listen. For method one, when we keep like stepping it up,
Yeah.
do we calculate the efficiency at like every step, or just do we get to the end and then?
Doesn't really matter. So when you record the data, like you record four different type of data. You can either do it while you're running the test or do it at the end of the test. Like the what's that called? Like the running efficiency, the running time of your code. That's there's another background information I should mention. Usually these tests are done through some sort of Python scripts, and like the efficiency of your coding doesn't matter. So you can do it either in the test or.
What's the point of doing like keep stepping it up a bunch of times? Like you get a slightly different efficiency at every test, right?
Sometimes.
So would your final efficiency be like an average or like the worst case? Or?
You might just get like a graph of efficiency. Maybe something like this for $1.
Okay.
This would be the efficiency versus IOT. Most of these kind of parameters also, it's like dynamic. The efficiency, or it's like the leakage current, or the can't think of anything else. But usually these two.
Does these much tests include like the response, like when a sudden like 5 amp drop, then what's the voltage surge response?
The sudden
Sudden current change. Like,
sudden current change is the second test of the load transient. Okay, and then
how do you test multi-phase if, like, for instance, you use multi-phase to achieve like 5 amps, but
for multi-phase box, usually you test it using the slew rate method. So you you configure a slew rate of the E load, and then let me think. It's still the same, but you're gonna use an oscilloscope instead because you want to measure voltage over time. So the waveform, it might look something like this. So this will be V out over I out. And I'm gonna increase the current limit to around, say 30 amps. That's usually what's common in multi-phase box. And V out, let's say, starts from 1.2 volts and then it drops at first, but when the additional phase is coming in, the voltage will pump up a little bit, and then it keeps dropping again, and then when the additional phase, let's say this is a 3-phase buck, then it'll drop like this, and then usually you wait for a little bit before want to decrease the current, and then it'll be symmetrical when you lower the output current. So, like that.
So how do you connect the setup if you're using a multi-phase?
The setup will be the same.
So it's just one VL terminal.
Just one VL terminal, one power wires, one wire to the oscilloscope.
Wait, before you I have a question too.
Okay.
Wait, so the slew rate is the change in voltage over time, right?
Slew rate is change in voltage. It can either be voltage or current. In the power supply, the slew rate is the voltage, but in the E-load, the slew rate means the current.
But like, wouldn't the speed at which it changes be based on how fast you're changing the current going through it?
Wait, say that again.
Because like what we're doing is we're slowly increasing the current and
Yeah.
seeing how much the voltage changes, right?
Yeah.
But if it's the change in voltage over time, then if you change the current quicker, then wouldn't the slew rate also change?
If you change the current quicker,
Yeah.
that would be another test.
Oh.
So this test, we are gonna change the current very slowly,
Okay.
usually as slow as possible. If you use the slew rate method,
So there's a different slew rate for each test condition?
there will be a different slew rates for each test condition. Let me think. For the slew rate, usually you want the catch is you really want to measure. You usually want to capture the screenshot on the oscilloscope, and sometimes you have to change the slew rate to make sure this whole waveform lands on the oscilloscope. If you using the same slew rate, sometimes they only capture like half of it, but sometimes capture the whole picture of it. So that's something. I guess that's why you want different slew rates, but I'm not too confident.
Okay.
Was stress testing?
Wait, say it louder.
Was stress testing and make a difference? Or like stress testing is always
Stress testing.
like turn it on for like 10 hours and or the VL be slowly degrading or it will keep the same.
No, I don't think I'm not too familiar with stress testing. And I think what you mentioned is more on the aging testing side. They usually, when they run their aging testing, they usually run the test over a couple of weeks, and they take measurements every hour. Yeah.
So this is a lot of tests we will have in the servo chamber.
Yes. For all of the testings, usually it's done across temperatures. So this test will be done in the servo chamber as well. To test the dots in different temperature conditions. Usually, for automotives, it's from -40 Celsius room temperature and to the I think 125 Celsius or 105 Celsius, but I'm not too sure.
Which one will have the highest VL, which one will have the lowest? Is there a time?
Yes, usually when you're at high temperature, the V out is more significant. Like the drop between like 0M and maximum I outload is more significant because the resistance is also a function of temperature. At cold temperature, the copper usually has less resistance. Yep. Good questions. I'm gonna need to drink some water.
I find it interesting they only test down to -40, where like you can go to Alberta and it would be colder. Or then for the heat, we go all the way up to like 100. We're like at that point in the oven.
Yeah, usually the 100 minus 40 is just like a industry standard.
Yeah.
It's usually those like, I think it's called QEC 100. You usually see those ratings. When you select, sometimes when you select DGK components, you see those like QEC 100s in the rating or something, or some AQC, I forgot.
There's a
Yes.
P in there.
And there's a Q in there somewhere.
I think it's ADQ.
Maybe. And that's rating, that standards, it means the part is rated from minus 40 to 105. And then for the load regulation, we also have another test called line regulation. For this test, it has really similar concepts as the load regulation test, except this for this time we are changing the V in, and then change V in, and then and fix I out. This is usually used if you have like some sort of battery as inputs. So for example, a 6S battery, it ranges from 6S, it's from 18 volts to around 20,
25.2.
25.2, okay, trust you on that. And then you just run, you can fix the I out, so I outs can be like different intervals, like 0 amps, 1 amp, 2 amp, 3 amp, usually bigger intervals. And then you just change the V out. Sorry, change the V in from 18 volts to 25.2 volts. And same deal, you're monitoring the V outs. And this test usually just to make sure the buck doesn't, like the voltage regulator or the buck or LDO doesn't shut down when the input voltage is too high or too low. Measure V out. Yes.
Does the previous test also conclude overcurrent protection?
Sometimes, yes. You can also include the overcurrent protection in the load regulation tests.
So
Do you just keep pulling current, increasing until it reaches the current limit of the dot?
So it's still using a slew rate.
You can also use slew rate as well. Both methods works. Any more questions? Okay, and that will conclude the first test. I'm gonna erase everything. Hopefully it's recorded.
Actually, I have a question.
Yes.
What
You can take a picture if I somehow didn't happen.
I forgot the yeah, actually good idea. But yeah, before we had the voltmeter connected to the output of the
Yeah.
DUT, was that V in or V out? Like, is V out the voltage across the load, and then V in is the voltmeter we had before?
So you mean like for this one? When I first mentioned
Yeah.
the voltmeter, it's connected to the V out. It's measuring V out,
Yeah.
and this. I think your question may be related to like how to measure the V in.
Like, I want to clarify what V in and V out is.
V in is the input voltage at the buck. Like, it literally is the
Okay, yeah.
is this V in right here at a buck. Then I have like switch node, ground, or like enable or like boot.
Okay. Yeah.
It literally measures at, if ideally you want to measure at this point, switch node to, V into ground.
Yeah.
Yeah, and then I probably should draw another DMM. Yeah, usually you need another DMM to measure the V. And then this.
For the multi-phase bump, is it beyond, like, for instance, like certain amps, like you have 3 phases, beyond like 10 amps that will turn on the first phase or or it's non-linear, like not how many phases you have to the amps, it's a linear.
I don't know this question. I don't know the answer to that question. Okay, no more questions? I'm gonna erase this one. And then, the next test is gonna be, it's called the load transient test. The concept is similar to the load regulation test, except for this time you're changing the current really fast. Changing the output as fast, not as fast as possible, but really fast. And so the goal is to measure V outs. How stable V out is. So this is goal number 1. Number 2, you also want to measure you want to test the control loop of the voltage regulator. So in the control loop is essentially like the negative feedback. Like in LDOs, it has this, I think it's called rec pin.
The ref?
Oh, yes, it's ref pin. And then in the buck, we have the feedback pin.
Wait, a audio is EDJ adjustable, it's not the
Yes, you're right. I forgot that was about this. And these 2 pins are doing the control system inside the regulators, and want to check how well the dot responds to a sudden change of output current. So the waveform of this test will look like this. So still have the V out over I out. Sorry, no. This will be over time. And you have two waveforms as you want to see. So, want to see the current step along. This will be the current I out on the oscilloscope, and then the V out. Sudden drop first, and then inductive spike, and then capacitive discharge. That's a terrible move. And then eventually it stabilizes again. It's not flat. And these 2 points should align.
Question.
Yes.
How do you force a sudden change in current if current is like drawn from the voltage?
Current is drawn from the voltage. You mean,
Like, wouldn't you have to make the current change? Wouldn't you have to change the voltage really quickly?
wait, sorry, say that.
In order to make the circuit draw current, don't you need to increase the voltage first?
You don't have to. You can change the impedance inside the
Oh, yeah.
electronic loads, and that will change the. Yeah, that will change the current. And for this time, I'm gonna use the dot as an LDO to make the explanation easier, because LDO has a simpler control loop. So for LDOs, we have C in, and then this will be a MOSFET going through a error comparator. So it will have negative feedback. This will be a reference voltage inside. This is connected. This is a just pin of LDO connected to feedback resistors. And you would have some output capacitors, and these output capacitors decides the waveform of the low transient response. So this resistor, capacitor, inductor in series is the C out. Because in the low transient test, the output capacitors ESR and ESL equivalent series resistance and inductance is significant enough, and it affects the voltage, output voltage response. So we need to model these in the analysis. This is ESR, and this is just C, and it's ESL. So now when you suddenly change the I out, you have the current inside the LDO cannot change. It takes some time for this control loop to respond. So the current has to come out from here, the C out, output capacitors, and we're going to call it IC out. And then we have some load here that is demanding the sudden change in current. I load can be something like turning on the camera or turning on like a game on the computer. And since this iReg from the LDO cannot change instantaneously, the current has to come from here, IC out. And we can write down the voltage, the V out equation based on these three elements here. The V out equals to the VESR plus VC out. I don't think there's a thing called ESC, so I'm going to write it as C for the capacitance there. And the voltage across this equivalent series inductance. And for the resistance, if we define I want to define going downwards as a positive. I'm thinking about why I do that way, but it just works. Hopefully we'll figure it out when I'm doing the analysis. And we can see if you're going down as positive, you have a negative current going through ESR. And you can see here, if the current is going this way, the voltage at this node between ESR and the capacitance has a higher potential than the voltage at this node. So this ESR is negative. And the capacitance is discharging through the plates. It's decreasing, but still positive. And for this equivalent series inductance, we have the voltage equation is equal to the inductor's voltage equation, di over dt. And since we define this going downwards is positive current, we have a negative current, say, let's say this is from the increase in current is from 0 amp to 5 amp. So this will be negative. The supply might all come from this capacitor. So it's negative 5 amp minus 0 amp over like a time interval, which is a positive number. So this results in this inductive spike to be negative. Like something negative, negative L times 5 over some time interval. So this in ESL will be negative as well. And if you think about it intuitively, the inductor there is trying to resist the sudden change in current. So it induces like a negative voltage across its intervals. So that's another way of thinking why this inductor is having negative voltage across its terminals. So we have this, we have a negative voltage from the ESR, which reflects to this instantaneous drop. So this is a ESR step. Right here. So from like this point to this point. Like from the old V out to this little peak. and the inductive spike will follow afterwards. So initially we have we have this big didt, so we're seeing a big spike going downwards, which is this negative part of the equivalent series inductance. So this is the inductive ESL spike. But after the didt is not changing anymore, it will recover to this part, and then this interval of V out dropping from here to there is the output capacitor discharging. It's simply because the V equals to Q over C, and this Q is decreasing, so V is decreasing as well. And afterwards, after we have this capacitor discharge, now the control loop comes in, and you'll try to recover, drag the V out back to what is supposed to be, and has some overshoot, and then eventually it stabilizes. Let me see. Yeah, and this is pretty much the theory about the low transient test. And most important part is why you're seeing this waveform. Any questions? Nice.
How do we change the impedance inside the
I'm gonna cover that idea later. And similar to the load regulation test, we're going to have a power supply to deliver power to the dots. And then we're also going to have some sort of load here, to E loads. But this time, instead of wiring it to a DMM, we are going to wire it to try to separate. We're gonna run it to an oscilloscope, because we want to measure the voltage over time and the current over time. So really similar setups, except changing the DMM to oscilloscope. Yeah, and I think this is it. Oh yeah, and then, sorry, one more thing. If you find like a problem with the low transient test, say if the voltage spike is too high, or the voltage, or if this peak is too low, then you can change the output capacitance you can increase the output capacitance. So we're gonna have this V equals Q over C, and if you change this capacitance, no, this is not a good way to explain it. So when you change the output capacitance, you have more charge. And when you have more charge, the charges left over on the capacitor will have more than before, which means you would have more V out. And Similarly, if you try to decrease the current, this waveform will just be flipped through this this V out line. So you have like a current step up and then ESL spike and then going down. So pretty much just this this waveform flipped horizontally. But if the issue, that's when the issue is related to this voltage spike. But if the issue is related to this control system, if this part is taking too long to recover, then you may want to change like the control system, modify the poles on zeros inside the voltage regulators. So I think that would be in the buck, that would be like some RC values at like these components here connected to a comp pin, and this is like a buck. Yep, and that's it about the low transient test. Any questions? Okay. And the last topic for today, I'm gonna try to cover some instrumentation stuff, like how the E-load change the current inside. But first, I want to start with like a concept. Usually, not power supply. It's often asked in interviews. Does anyone know what this concept means? Four-wire sensing. It's usually related to the power supply. It comes together with power supply. Or another name of it, I think it's called Kelvin sensing.
I just learned this last term and I already forgot.
Yes?
Like current sensing with like basically you use like a shunt resistor and you use like kind of like an analog, like a differential pair. Is that
No.
no?
Okay, I'm gonna give the answer. So this four-wire sensing is pretty much because the power supply, say it's a voltage source. Voltage source should be. Voltage source, but you have some wire similar to the concept of why E-load has like a voltage drop across its terminals. Like the voltage measured at the E-load is smaller than the actual buck V outs. The voltage, the power supply, it only tries to measure the voltage at this point. Like this is inside, this is the whole power supply. And when you run a test, you're gonna use the wires, and the wires have parasitic resistance. So it will create a voltage drop at a time. By the time you reach this, let's call this node buck V in. No, actually I'm gonna call it dot V. So this R wire, say this point is measured for, say, 12 volts here, but by the time it reaches .Vn, it's gonna be like 11.5 volts because it has some voltage drop here across the wire. So the solution is to measure, instead of measure voltage at this point, you're gonna run another wire and measure the voltage at this point. And this will be ground. This should be drawn to ground. And there's some resistance here as well. So really similar to the concept why we need to change, why we need the DMM to measure the load regulation, to measure the Vouts when we're running the load regulation test. We need a wire to measure the input voltage and then adjust this power supply to deliver the rated Vin. And this would be our wire as well. Yes.
Don't the other wires have like parasitic resistance as well?
It has parasitic resistance, but the current is 0.
Yeah.
So there's no voltage drop in that one.
Makes sense.
And the next one, this is about the power supply, and for the E-loads, I'm gonna draw the internal circuits. So for an E-load, you have two terminals, positive and negative. They're going to go through a MOSFET controlling the resistance, and then a resistor to ground connected to the negative terminal. Then this resistor is, oh, sorry. This is essentially what's inside the electronic mode. So everything here inside the dashed line is in the E-load. And we're going to label this RFET. And this one's labeled as R shunt. And this is a voltage source. The equation would be I in times R shunt. This will be a dynamic voltage source, something this IN is going to be a digital signal. R shunt is a fixed value, and the E-load knows this value. So inside the E-load, it can perform some calculations and calculate how much this voltage source needs to be. So for this example, I'm going to say this is going to be 1 ohm. IN is set to 1 amp. So at this node, it's gonna be 1 volt because IN flows in this direction, and this reference voltage, because IN is set to 1 amp times 1 ohm, will also be 1 volt. Okay, and now let's say we want to adjust the IN. So we want to increase the current from from 1 amp to IN to 3 amp. And so this voltage source changed its input, changed the its terminal to 3, changed this V plus now equal to 3 volts. But this V in this V in is this V minus was still 1 volt. And because we have a difference here, it's gonna send a more positive voltage signal to the gate, so that will decrease the MOSFET's RDSR. So that's the on resistance between the drain terminal and the source terminal. So essentially from this point to this point. When you decrease the resistance, if you decrease the resistance, if the R goes down, V stays the same, and then I will go up. So this is how you change the current inside the ELODs. Yes.
For ELO, the limiting factor is the power rating of the Armstrong, or the value, or the tolerance plus the value of R. Like, for instance, some ELOs last for like max 5 amps, some say like 50 amps.
I understand. From my understanding, it's a mix between R shunt, like the thermal dissipation power it can handle, and also the voltage, the input voltage. I don't. I'll explain.
So the input voltage,
Like input voltage between these two terminals. Let's say if you have like a really small input, say Vin equals to 0.5 volts. Like by the time the wire reaches the load, the input voltage observed across terminals is only 0.5 volts. And you want to load, let's say 10 amp. You want to do some stress testing. You want to do 10 amp. So this voltage, let me see if I wrote this down. I did not. This part of it is the 0 times 1 ohm, but usually it's gonna be inside the ELOD, it's not gonna use 1 ohm resistor, it's gonna use something pretty small, like 0.01 ohm. So at this point it's 0.5 volts. And at this point it won't be 1 volt anymore. It will be .1 volts. But I think the problem is for this RFET, the VDS has some limits. The VDS needs to be larger than like VDS minimum. And this will create will induce limits on the V. But I didn't choose a really good number, so the difference right now 0.4 volts. Probably you can still go slower, but if I choose the numbers right, you may see something like 0.1 volts, which is not enough to to pass through a lot of current through this RFET, through this MOSFET. We're modeling as you can also model this as a variable resistor. So essentially, the E load is just a variable resistor that controls the amount of current passing through. Yep. Any more questions? Okay. And then last instrument I really want to introduce. It's called a source measurement unit. I'll take a seat. So for this source measurement unit, it can operate in 4 different quadrants. So we have positive voltage, negative voltage, positive current, and negative current. And we're going to deliver current to be positive. So in other words, sourcing current. Is positive and sinking current is negative. And for the voltage, if you're if it's providing a positive current like a power supply, that would be a positive current. Positive voltage. And if it's consuming voltage, like some resistors, it's consuming voltage across its terminals, it will be a negative voltage. So source measurement unit, it can operate in all 4 different regions. So in the first quadrant, we have power supply, which is delivering currents, is sourcing currents, and at the positive voltage. And E load is on the opposite side, on the third current. It's consuming voltage and sinking current. And in the second quadrant, you can have something like a voltmeter. It's sinking some currents, very little currents, around 0.1 or less than 0.1 milliamps. But it's reading a positive voltage. It's trying to read a voltage, so it's in the second quadrant. Delivering currents, sinking currents. Sorry, I think I'm wrong. This should be in the DMF, so that will also be in the voltmeter, so the DMF. It will be also in the third quadrant. And then in the second quadrant, if you have something that's consuming voltage but is delivering current, it's just like a current source. So I can't really think of a device, but similar to like a current source. If you do something like nodal analysis, you have current source and a bunch of resistors, and if you draw your circuit weird enough, you might see something like negative, positive like this. But usually I don't know what device it happens. But my point is,
Photodiode?
sorry,
Photodiode or photoresistor? Or photodiode?
I don't know. I don't know what that is. So
It's like when light hits it, it creates current.
when light hits it, it increases currents.
Yeah, you can use it as a sensor.
It's not a current source.
I think it is.
Like thinking. Delivering currents. Yes, delivering currents and then
Sinking voltage.
thinking voltage, assuming voltage. Maybe, I'm not too sure. I don't. A diode?
If something
But
delivers,
diode will be still in this region.
if something delivers current, doesn't it also have to have a positive voltage?
Yeah.
Or does it?
Yeah. Yeah. This is kind of strange. I'm not. Let's just erase this part for now because I'm not sure if it's right or not. I can be wrong. So. But my point is, you can combine all the instruments into one single instrument. But let's not worry about the second and fourth quadrant for now. It's going to combine the power supply, electronic load, and EMF into one single instrument. So when you're running the test, you usually write the Python scripts. So you don't need to write scripts for 3 different instruments. You only write scripts for just one big instrument, which is commonly used in the industry. It's really expensive. So only like the big companies can afford this. We don't buy this stuff.
Our cheap little AliExpress one can't do this?
No, I think also the source measurements comparing to the V-loads, it's getting rid of this. It's getting rid of this resistor. It just uses like a transistor, a MOSFET, to control the impedance, so it controls the current drop. So that's it's gonna be more complicated. I can imagine replacing a resistor. We can replace this shunt part with some advanced circuits called current mirrors. If you guys heard of it. A current mirror is something like have a voltage source, and then it goes into some let's say it was an NMOS, but you're connecting the gates together, and then you have some other circuits, and you can cascode or cascade it to measure to scale it up and scale the current up and down. And how it works is pretty much this. This gate is the same. The gate is VGS is at the same voltage, and the transistor, some semiconductor, what's that called? Semiconductor properties are the same between these two. So the current flowing here will be reflected to the current flowing there. Yes.
Does it only work with BJTs or also FETs?
I'm not too sure about BJTs because I never learned about them.
Is this like a property of just FETs as well?
This usually, I believe you get two equivalent BJTs will also work. but I'm not too sure on that.
Yeah.
For the MOSFET, it'll be a MOS. And then you can have some. And have another, like say, PMOS. Keep going, I just keep cascading. So, like something like this will be inside this source measurement unit, and there'll be like, it'll be really complicated. If you search up like E-load PCBs, like we have one over there, it's the AliExpress one, and if you search up source measurement units, it's gonna be like, it's gonna look like some computer's motherboard.
And so what we have is not a source measurement.
No, it's not. And the block diagram, this is like a simplified block diagram. The SMU, the source measurement units block diagram will have like more of these op amps, comparators, and more. It's just more complicated. So it'll be much bigger. Like this, we'll have like 5 components. Source measurement units will have like 20 more. But it's powerful. And also this response time, like it also responds faster. You can pull for the E-load. It has like I think it has a slew rate limit on the E-load, so it has a limit on how fast you can change the current. The source measurement units, it can respond faster because you're getting rid of this resistor. Like the RC part is off, it's away. Like an RC circuit introduce a time delay. I believe that's how it works. Yep, and that's it about this presentation. Hope you guys learned a lot.
That was good. And thank you for everyone